second page, or part 2 of the VSEPR notes, and now we're going to look at what happens if we have 4 electron regions around a central atom. So again, this is the electron region geometry here. So we have electron region. And then the other column over here is the molecular geometry. Let's look at methane. If we draw methane, we have this particular arrangement. And if we look at this in the plane of the paper, it looks like each one of these is 90 degrees apart. However, we're in 3 dimensions. So in reality, this is 109.5 degrees apart, with each of these being the corner of a tetrahedron, and then this would be in the very center. Since each one of these corners is represented by an atom, our molecular geometry for this is also a tetrahedron. And if we tried to draw this in 3 dimensions, we'd have the hydrogens looking more like this around the central atom. And the angle would be 109.5 degrees. Let's take a look at NH3, or ammonia, putting nitrogen in the center. We still have a lone pair. So this lone pair is going to occupy space. So let's draw that by showing that it's going to occupy space. If we try to redraw this electron region geometry, we would have a lone pair up here. So I'll show that it's kind of occupying a balloon up there. And then we have the 3 hydrogen atoms connected to the nitrogen. So we have this, this, and this. This is a lone pair now. So our molecular geometry is called pyramidal because it looks kind of like a pyramid. And we have the nitrogen, hydrogen, 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 and then at the very top of the pyramid we have this lone pair. Now remember, lone pairs are going to compress these angles, so instead of being 109.5, the angle is compressed to about 107 degrees, depending on what you have down here. Let's take a look now at H2O, water. If we draw the Lewis structure, one way we can draw it is like this. We look at this and we say, aha, this is linear. That looks like this draws and makes a nice line. But remember, we are in 3 dimensions, not 2. So let's take this, and one of these is going to be replaced by an electron pair, and another one is going to be replaced by an electron pair. So if we do that, we get something that looks more like this. So we have an electron pair on the top, and then off to this side we're going to have another electron pair. So really, when we go to draw this, we should show this as a bent molecule. With 2 lone pairs on the oxygen. So here we had it in 109.5 degrees. A single lone pair squeezed the angle to 107, so 2 lone pairs is going to squeeze it still farther or further, and it's going to be roughly 105 degrees now. So if we outline just the shape of the molecule, we have this. This is another bent triatomic geometry with an angle of 105 degrees. So this is a bent triatomic. Bent, tri, meaning 3 atoms. So 3 atoms, and it's bent. Let's take a look at how to figure out molecular geometry. The first thing you're going to do is draw the Lewis structure. The second thing is determine the electron region geometry. And finally, from that, you'll determine the molecular geometry, which is based strictly on the atoms. So let's try these 4 down here, and just to make this a little more challenging, let's make this SO2, sulfur dioxide, instead. So scribble out that, make that SO2 instead. Let's do this one first. I want you to draw the Lewis structure, and then we'll discuss the geometry. You should have counted that there were 20 electrons. Remember to add 1 because this is an anion. And this should have been your Lewis structure. You have 4 regions around your central atom. 1, 2, 3, 4. So your electron region geometry is going to be tetrahedral. However, what we're really interested in is the molecular geometry. And in this case, what we're going to have is bent triatomic. Let's try ammonium next, NH4+. In this case, you count the valence electrons, 5 from the nitrogen, 4 times 1 from each one of the hydrogens, but you have to subtract an electron because this has a positive charge. So you end up with 8 electrons. When you draw the Lewis structure, you get this. So you have 4 electron regions around the central atom, which means you'd have a tetrahedral. You have 4 atoms around the central atom. So this means that your overall molecular shape is tetrahedral. Let's try sulfur dioxide. This should be your Lewis structure for sulfur dioxide. You have a total of 18 electrons. If we count the regions, and let's go ahead and highlight those, we have 1 region here, we have another region here, we have another region here. We have 3 electron regions around a central atom, so the electron region is going to be trigonal planar. However, one of those regions is an electron pair, so we're going to be looking at just the shapes of the atoms. So this ends up being another bent triatomic. So both of these are bent triatomics. However, here the angle is going to be about 120 degrees, whereas in this case the angle is going to be about 109.5 degrees. So that's the difference between the two. Last up, let's do the phosphite anion. Here we have the phosphite anion. We have a total of 26 valence electrons, 5 from phosphorus plus 3 times 6 for our oxygens, and then another 3 to account for the -3 charge. Here is the Lewis structure. Let's count the number of electron regions around the central atom. We have the electron region due to the lone pair, with the electron region due to each one of the bonds. So we have a total of 4 regions around the central atom. So this is tetrahedral in terms of our electron geometry. But what we're really interested in is the molecular geometry. So in this case, our molecular geometry is pyramidal, or pyramidal, depending on how you want to pronounce it. So as we finish up, let's draw a big red circle around each of the final molecular geometries. So the first one here was bent triatomic. The second was tetrahedral. This was another bent triatomic geometry. And this one was a pyramidal molecular geometry.